Hello guys, welcome back to another lecture in this course. In this video, we shall be looking into vectors and vector operations. A vector is a quantity that has both magnitude and a direction on a vector space. For example, an aeroplane is traveling to the west at a speed of 200 kilometers per hour. So here, the magnitude is the speed, which is 200 kilometers per hour, and the direction is the west. If we are to represent this information on an xy plane or a vector space, we draw a simple illustration like this. This is the original point where the plane is starting to move, and it is moving towards this direction to the west. And this is the end point where it is representing the direction of the vector with an arrow in it. And we are saying the movement of the plane is 200 kilometers per hour. And this 200 represents the magnitude in which the plane is moving. And also now magnitude can also call the length. Magnitude can be called the length. So in vector space, we are saying OW from point of origin up to W, we represent a vector with an arrow on top, is equals to 200 kilometers per hour. So we are saying from point of origin, this vector is moving at a magnitude of 200 kilometers per hour. In this case, a vector also can be represented using coordinates within a dimensional space. For example, we can represent a vector OA, which is having coordinates 2 and 3. This obviously it's called X, this will be Y. So if you are drawing a plane, this is our Cartesian plane. This point it's X. This point it's Y axis. So if you are drawing our vector, this is the vector direction. At this point here we have 2, and also on the Y axis we have 3. This will be point A. This will be point O, point of origin. 2, 3. So this OA is called position vector. It's called a position vector. A position vector. So this position vector OA, it has what we call horizontal components and vertical components. So the horizontal components of this vector are, for the horizontal components are 2 and 0, where 2 here is represent the x-axis. And also the vertical components are 0, 3, where 3 is the y-axis. So we are saying we have vertical components and the horizontal components, and this is all part of the position vector. And as you can see here, this is a two-dimensional vector, as you can see. And we can also construct a three-dimensional vector, a vector in 3 dimensions. And it will have coordinates 1, 2, and 3. This is a vector which is a 3-dimensional vector. And if we are to plot a 3-dimensional vector, it means the vector will have coordinates like x here, y here, and z here, where this will be our x, this will be our y, this will be our z. So it is possible, if you are having a good software, we can construct a 3-dimensional vector. And vectors, they are represented in a column or can be represented in a row format. And in a row format, for example, we have vector 1, it can be represented in an array, which is a row format. For example, we have vector 1 and vector 2. And this list can go up to vector n. And this same vector, like I said, we can represent these same vectors in a column way up to vector n. Now, let us take a look into vector operation. We only solve vector algebra if they are of the same dimension. If they are from same dimension, 2 dimension or 3 dimension. So let us start by addition. Addition and subtraction of vector. So when you are doing addition and subtraction of vector, you should make sure these vectors are within the same dimension. Let us see heavy coordinates. Assume we have vector 1 with the coordinates in 2 dimensions, 3 and 2. And also we have vector 2, which is also in 2 dimensions with the 1 and 3. So to add these vectors, we have to simply say vector 1 plus vector 2. We have to add the x coordinate, which is x1 and y1. And also here, this is x2 and y2. So we have to add the x1 plus the x2, which is 3 plus 1. Put a comma to separate our coordinates. y1 plus y2, which is 2 plus 3 here. And also finally, we have these 2 coordinates, which is 4 and 5. And these 2 values represent a new vector. We can call it even vector 3. So it gives us a new vector. The addition, the sum of the 2 vectors gives us a new vector. Okay, then we can subtract the vectors. Let us subtract v1 minus v2. v1 minus v2, we are saying we are having coordinates 3, so x1 minus x2, and also y1 minus y2, and which gives us 2 and minus 1. So this is our new vector. So if we are to plot this graph, for example, for addition, we need to plot to represent this on a graph. We are saying this is x, this is y. So if you are to represent this on a graph, assuming this point is our position vector v1 with coordinates 3 and 2. And this is our vector 2, our position vector 2 with coordinates 1 and 3. The addition of the 2 gives us a new vector, which is a position vector 4 and 5. Let us call it v3. So this is the combination of the 2. So we can represent this on a vector plane. So if we are to write in a formula way, we are saying vector v1 is equals to x1, x2, up to xn. And also vector position 2 is equals to y1, y2, up to yn. And this sum, if we are to add these two, if we are to add these 2 vectors, we are saying vector 1 plus vector 2 is equals to x1, which is x1 plus y1, x2 plus y2, and this goes on and on up to xn plus yn. And we can do the same for subtraction of vectors. Let us dive into the dot product or the multiplication of vectors. So let us take a look into a position vector. So given v1, our position vector v1 is having coordinates 3 and 2, and also v2 position vector is having coordinates 1 and 3, which are all real numbers. Okay? So for dot product, we are saying v1 position vector v1 dot v2 with an arrow at the top to represent vectors. So we are multiplying x1, y1, x2, y2. So here we are multiplying 3 dot 1 multiplying x1 dot x2 plus 2 dot 3. Now we finalize our answer 3 plus 6, which gives us a total of 9. And also, if we are to do for three-dimensional vectors, assuming we have a vector u with the coordinates 1, 2, and 3, and the vector v with the position vector 0, -1, and 2. If we are adding the two, u position vector dot position vector v is equals to, same applies, we multiply x1, y1, z1. Here x2, y2, and z2. Now we are saying 1 dot 0 plus 2 dot -1 plus 3 dot 2. Finally, here we get 0 minus 2 plus 6. And our final answer is 4. So this is how we do dot multiplication of vectors. And also we can write the formula as follows. For example, we are saying u dot v, this position vector, is equals to summation n I equals to I equal to 1, component of vector u, and also components of vector I. So here we are saying u here represent our first vector, position vector, and this our second position vector. N represent the number of dimension of the vector, the dimension of the vector space. ui here is just representing the components of the vector u. So I want us to take a look into magnitude. Magnitude can be length. Remember on my introduction when we talk about an aeroplane which was flying due west. So we discovered that the speed, which is the magnitude, was also representing the length. So magnitude can be called length. So the magnitude of a vector is just to represent a scalar quantity which is calculated using the formula. Example, v1 is equals to position vector xy, where we are saying v1 with the position vector xy will represent a Pythagoras theorem, x square and y square. For example, let us find position vector 2 with the values -3 and 4 on a vector space. So the magnitude is represented by this symbol here. So v with the direction for the direction vector here. Okay, so here we have to remember to put this to represent the magnitude. Let us find the magnitude of v2. So v2 like this, and this represents the magnitude, is equals to the square root of -3 square plus 4 square, which is equals to root of 9 plus 16. Then if we add the 2, 9 plus 16, we get 25. And the square root, it gives us 5. So the magnitude of v2 here is 5. If it is a vector in 3 dimensions, it is the same. For example, let's say vector 1 is equals to position vector. This is our position vector 1, 2, and 3. So if it is in 3 dimensions, to find the magnitude, we do the same thing. Square root 1 square plus 2 square plus 3 square, which gives us the square root of 1 plus 4 plus 9, which gives us a total of, here this is plus, which gives us a total of 14. That's our magnitude. We can find the square root of this number, then we can write here. That will be our magnitude. Let us also take a look into angles between two vectors. For example, we are having a vector position 6 and 8. In this vector, if we are to put it on a vector space, x and y, we are saying that this point 6, this point is 8. This is the angle it makes. Okay, this is the angle it makes. And also, if you are to look into it, the magnitude of this vector is 10. So the position vector v is having an angle theta here. So the question, how do we find this angle? To find this angle in mathematics, according to trigonometric ratios, we use SO, CA, TOA, where this is sine, which is equals to opposite over hypotenuse, which is our longest side there, and the opposite side. So we have opposite side, which is 8. We have the adjacent side, which is 6, and the longest side here, which is 10. And also this is cos, which is represented by A for adjacent, H for hypotenuse, and also here it's tan, O equals to opposite, A equals to adjacent. So this formula can help you to find this angle using trig ratios. In a vector space, in most cases, especially in machine learning, we have a method that we use to find angles between two vectors. Given position vector u and position vector v, the most common formula which is used is theta. Theta is equals to cos inverse bracket position vector v and position vector u and position vector v all over the magnitude of u dot the magnitude of v. So this is the formula which is normally used. Let us try to calculate the position of a given angle. For example, given a position vector, u, 3 and 2, and position vector v equals to 1 and 3. So if you are to represent this on a vector space, assuming we are saying this point is position vector u, where we are having 3 and 2. Okay, assuming here it is our position vector v with the points 1 and 3. So angles between the two vectors is this one. This is the angle theta that we are looking for. So to find the angle of two vectors, we use this formula that I have written on above. We use this formula. So to use this formula now, what we need to do first is to find the dot product. First thing that we need to do is to find the dot product. So to find the dot product of position vector u dot position vector v is equals to, we have to multiply 3 dot 1 plus 2 dot 3, which gives us 3 plus 6, and which gives us a total of 9. That's the dot product. And now also secondly, we need to find the magnitude. find magnitude, which is also the length here, to find the magnitude, which is also the length. So to find the magnitude, let us start by finding the magnitude of position vector u, which is equals to square root of 3 and square root of 2. So it's 3 square plus 2 square, which gives us a root of 9 plus 4, which gives us an answer of square root 13. Same applies also, we can find the position vector v magnitude is equals to the square root of 1 square plus 3 square, which gives us square root 1 plus 9, which gives us a total of square root 10. Now, what's left is to take these values that you have calculated here, and substitute it to our equation, to our formula. So now let us substitute to our formula. Let's say theta is equals to cos inverse 9, which is our dot product, over the magnitude. So our magnitude is 13 dot magnitude 10, which gives us cos inverse of 9 all over 13 times 10, which is 130. Now, cos theta is equals to cos inverse. Here, if you find cos inverse of this number, we get 0.789352, and it goes on and on and on. Now, what we need to do is to go on our mathematical tables, or we use a calculator to find cos inverse of this number, which gives us 37.87, and it goes on and on. So this is the angle, the theta, the value of this angle. This angle theta is represented by 37.87 degrees. So this is how we find angles between two vectors. Let us also take a look into linear combination of vectors. A linear combination of vector, or of two or more vector, is the vector obtained by adding two or more vectors by multiplying with a scalar. Let us take a look into linear dependent vector. Linear dependent vector. So on linear dependent vector here, we are looking into a set of vectors which are linearly dependent if there is a linear combination of the other vectors. For example, we have to check if we are given two vectors. Is there any linear combination between those vectors? For example, we have a set of vector. Let us call it S, a set of vector. In this set of vector is having vector 1, which is having this vector position, let's say 4, 6, and 3. And let us say we have vector 2, which is having this vector position 3, 4, and 5. These are the components of the vector. Then let us say we have vector 3 with the following components, which are 7, 10, and 8. These are the components inside the set. So here we can see that these three vectors are linearly dependent if combining v1 here, if you combine v1 plus v2. For example, if you are to see v1 plus v2, it gives us v3, which is 7. 6 plus 4, it gives us 10. 3. So if you add these components, we can see that it gives us v3. So we can say that these vectors, these three vectors, they are linear dependent vectors. So v1 and v2 is equals to v3, as you can see. And if you are to represent these vectors on a vector space, we can actually see that, for example, this is just an example. The vectors will be on this vector space. This V3, this will be V2, this also will be V1. They are linearly dependent. Let us take a look on a linear independent. This is linear dependent. These vectors, they are dependent to each other. There is a common relationship between these vectors. Linear independent. So we have what we call linear independent vector. So linear independent vectors are vectors which are not depending on each other. For example, consider for linear independent, we have, for example, vector 1 is equals to 1 and 2. Then vector 2 is equals to 3 and 4. So here there is nothing which is linearly depending with each other. Yx. So if you are to represent this on a xy plane, we can see that this is vector 2, which is having 3 and 4, and this probably is vector 1, which is having 1 and 2. And also we can have vectors. For example, we can have vector 1, which is in 3-dimensional space, and these are the components 0, 0, and vector 2, which is 0 and 1 and 0, vector 3. So there is nothing which is dependent, which is dependent here. All values are independent, as you can see. So if we are to write a formula for this linear combination, if you are to write a formula for this linear combination, we are saying that a set of vector V is having V1, V2 up to Vk, where k represent the scalar. And also a new vector with a linear combination. Now, if you are to plot a new vector with a linear combination, we are saying our set will have lambda, let's say lambda 1, which represent our scalar V1, plus lambda 2 V2 plus lambda 3 V3, and this can goes on up to lambda k Vk, and this is all for how we can search or how we can check the linear combination so that we can obtain the scalar value. So these lambda 1, lambda 2, and lambda 3 that you are seeing, these ones up to lambda k represent the scalar. These are scalar. So for example, if you are to take V1 with the components 3, 2, and minus 1, V2 with components 1, 1, and 0, V3 with components 3, 7, and 5. We can write this using scalar. We can have alpha V1 plus alpha, let us say this is alpha 1, alpha 2, V2 plus alpha 3, V3, and all these are position vector equal to alpha 1 bracket vector 1, which is 3, 2, minus 1, plus alpha 2 bracket 1, 1, and 0, plus alpha 3, which is our last vector 3, which is 3, 7, and 5. So after doing so, our new vector is equals to alpha 1 times 3. Here we get the position vector 3 alpha 1 plus alpha 2 plus 1. So here we get alpha 2 plus alpha 3 plus 3, we get 3 alpha 3. Now here alpha 1 times 2, we get 2 alpha 1 plus alpha 2 times this, we get alpha 2. Then alpha 3 times this, we get plus 7 alpha 3. In our last coordinate, we are just saying alpha 3, we are just saying alpha 1 times minus this number, we get a minus alpha. Alpha 2 times 0, we get 0. Then alpha 3 times this, we get a plus 5 alpha 3 as our new vector. So this is just a simple math where we are just adding this number. This 3 plus 1 plus 3. 2 plus 1 plus 3. But now we are adding alpha. So this will be alpha 3. It will be 3 alpha 1, 3 alpha 2, 3 alpha 3 for scalar numbers, for scalars. So in other words we are saying if given, maybe let's say vector 1 is equals to 1, 0, 0, and vector 2 is equals to 0, 1, 0, and vector 3 is equals to, so these are our components 0, 0, let's say 0, 0, 1 to make it an identity matrix here. So for alpha 1, alpha 2, and alpha 3 here, we are just simply saying our new vector, we are simply saying for identity matrix here, the identity matrix will be alpha 1, then 1, 0, 0, plus alpha 2, 0, 1, 0, plus alpha 3 for our identity matrix, which is 0, 0, 1, and also our identity matrix is equals to 0. So this forms an equation. So I think this is all for this lesson. Let us take a look into how we can perform vector operation using Python. Okay, let us take a look into vector operations using Python. So the first thing that we need to do is to import the NumPy library, which is part and parcel of Python NP. We are going to store our vector inside V. So V is equals to NumPy, our library, this we have imported, dot, we need an array. So we are going to use a 3-dimensional space. So 4, 6, and 3. These are our vectors. And let us say we have vector U. Let our vector be U and V. So vector NumPy.array. And we are going to have these components 3, 4, and 5. What we need to do with these vectors, we are going to perform addition. So to perform addition of these vectors is just simple by just print V plus U. Let us say here, let's say addition. So this is for addition. So this is for addition. If we add 4 plus 3, we get 7. 6 plus 10. 6 plus 4, we get 10. 3 plus 5, we get 8. So this is the addition of the vector. And also, if you want to subtract the vectors, it's a print. Let us subtract V minus U. We get these values. 4 minus 3, we get this value. 6 minus 4, we get 2. 3 minus 5, we get negative 2. And same apply also if you want to find the scalar multiple here. The scalar multiple of the vector, we can just say print 2 as our scalar times, let us find the scalar for vector V. So our vector V, if you multiply by 2, we get okay, we can't see our vector V. Let us say print V here so that we can see how actually scalar works. So we multiply by 2 becomes 8, by 2 becomes 12, by 3 becomes 6 because this is V. And lastly is to find the length. or the magnitude of the vector. So to find the length of a vector or the magnitude, here we just say print NumPy dot length. This is linear algebra algo. So linear algebra dot num. So this is how we get the length, the magnitude. Then we run our code. Then we get the magnitude. This is the magnitude of vector v. And if you are to get now the dot product of the two, dot product. If you want the dot product, it means we can say our variable, let us store it on dot, is equals to NumPy dot, let us call the dot class or the dot function. Then we want to multiply v and u. Then we print dot, our variable. Then we can get so this is the dot product of these two vectors, as you can see here. So we can do a lot of computation of vectors using Python, but I think for our lesson this is enough. See you on the next lesson where we shall be looking into matrices. Thank you for watching. Bye-bye.